first thing I want to talk about are cat-1 spaces. But before that, let me just, this has probably been done already, but let me just briefly recall a few basic facts about hyperbolic n space, Hn. So Hn can be characterized as the unique, complete, simply connected Riemannian manifold of constant sectional curvature equal to -1. So here unique means unique up to isometry. Complete means that any geodesic can be extended indefinitely in both directions for all time. And simply connected, I suppose everyone knows what that means. Okay. And there are many models of the hyperbolic n space, but two standard models are the unit ball model and the upper half space model. So maybe Krishnendu has covered this.
Yes.
So the unit ball model is the open unit ball in Rn with the metric equal to the Euclidean metric dx1 squared plus dxn squared times a positive smooth function 4 divided by 1 minus norm x squared whole squared. Okay. And the upper half space model is the upper half space in Rn. So that means the set of points in Rn whose nth coordinate is positive. And here the metric takes the form Euclidean metric divided by the last coordinate xn squared. So the height squared. Okay. So here are pictures of the ball model and the upper half space model. And in these models, if you take the topological boundary inside Rn, then for the ball, the boundary is Sn minus 1, the unit sphere in Rn. And for the upper half space model, you should really take the boundary inside Rn union infinity in the 1-point compactification of Rn. And there the boundary is Rn minus 1 union a point at infinity. So this is also topologically a sphere, as in the ball model. Okay. And the geodesics then, in the ball model, the geodesics passing through the origin are diameters, as you can see, like this diameter here, which intersects the boundary at right angles. And otherwise, if they don't pass through the origin, then they are arcs of circles which intersect the boundary at right angles. So like this arc of circle, which intersects the boundary at right angles. And in the upper half space model, the geodesics, well, if they end at the point at infinity in the boundary, then they are vertical lines, like this vertical line. This goes up and ends at the point at infinity and is perpendicular to the boundary here. And otherwise, they are arcs of circles which are perpendicular to the boundary. So these will be semicircles which are perpendicular to this boundary Rn minus 1. Okay. So these are the geodesics in the ball and half space models. And to talk about cat-1 spaces, first of all, we just need to understand in 2 dimensions, the 2-dimensional hyperbolic space or the hyperbolic plane. So we need a couple of basic facts. One is that given any 3 non-negative real numbers ABC, which satisfy the 3 triangle inequalities, A plus B bigger than C, B plus C bigger than A, C plus A bigger than B, there exists a unique geodesic triangle in H2 whose side lengths are exactly ABC, where as usual unique means up to isometry. Okay. So we have existence and uniqueness of geodesic triangles with prescribed side lengths satisfying the triangle inequalities. And we also have what's called the hyperbolic law of cosine. So if I take a geodesic triangle like this, So the side lengths are A, B, and C, and the angle at the vertex opposite the side C is theta, then we have this law that cos HC is cos HA cos HB minus sin HA sin HB cos theta. Okay, so this will be important for us, this hyperbolic law of cosine. So now I can come to what is a cat minus 1 space. So you might have talked about curvature of manifolds and sectional curvature of Riemannian manifolds. So Riemannian manifolds are, in particular, they're smooth manifolds. They have a smooth structure. But cat minus 1 spaces is a notion of negative curvature for metric spaces. So they need not be smooth manifolds. In fact, there are many examples of cat minus 1 spaces which are not manifolds. Okay. So this is a purely metric notion of negative curvature. And it is the following. So XD is a metric space. We say it is cat minus 1 if, first of all, X is what is called a geodesic metric space. So any 2 points can be joined by a geodesic. So what does that mean? That means given any 2 points X, Y, and X, there exists a geodesic in the space joining X to Y, where what is a geodesic in a metric space? So it's a map gamma from an interval in R into X. So gamma starts at X and ends at Y, and it satisfies, it's an isometry from an interval into the space. So the distance between gamma S, gamma T is equal to mod S minus T for all S and T. Okay, so it's an isometric embedding of an interval into the metric space. Okay, that is a geodesic in a metric space. So we require for a cat minus 1 space that any 2 points can be joined by a geodesic. And the main requirement is that, so once we have geodesics in the space, we can talk about geodesic triangles. So that means, like in this picture, 3 geodesics whose endpoints match up. Okay. So what we require is that geodesic triangles in X are thinner in a certain sense than geodesic triangles in the model space H2. So what does that mean? That means, first of all, you take a geodesic triangle, X, Y, Z. So delta, this is a geodesic triangle in X. So then you look at the distances from X to Y, Y to Z, and Z to X. Those are 3 numbers ABC which satisfy the triangle inequalities, because X is a metric space. So therefore, by the fact we just mentioned, there exists a unique triangle in H2 which has the same side lengths ABC. So this triangle is called a comparison triangle, delta bar. So there are vertices X bar, Y bar, Z bar corresponding to X, Y, Z. And now we want the triangle delta to be thinner than the triangle delta bar in the following sense. So if I take any 2 points P and Q on the sides of the triangle in X, then I can find corresponding points on the sides of the triangle delta bar. So points P bar and Q bar. So as in this picture, such that the distance of P bar from X bar is the same as the distance of P from X, and the distance of Q bar from X bar is the same as the distance of Q from X. Okay, so these are comparison points, P bar, Q bar. And then what I want is that the distance in X between PQ is less than or equal to the distance in H2 between P bar and Q bar. Okay, so this is what is called the cat minus 1 inequality. All right, so in this sense, this triangle is thinner than the comparison triangle in H2. Okay. And we can also, once we have comparison triangles, we can talk about comparison angles in our metric space. So the comparison angle, I'll denote it by angle minus 1 YXZ. So this is the angle at X formed by the points Y and Z. This is defined to be the angle, the hyperbolic angle at x bar between y bar and z bar. Okay, so this is a real number between 0 and pi. Okay. And so the first consequence of the cat-1 inequality that we can find is that, so we said that there are geodesics joining any 2 points in a cat-1 space, but in fact, the geodesic joining any 2 points is actually unique. Okay, so this follows from the cat-1 inequality, because suppose I take 2 points x and y, and I have 2 geodesics, say gamma 1 and gamma 2 from x to y. Then what I can do is, if I take any point on the top geodesic, say gamma 1 of t, let me call that point z, then I look at the 3 points x, y, and z. So these form a geodesic triangle, right? So I can look at the corresponding comparison triangle here. X bar, Z bar, Y bar. Okay. And then what I notice is that in this comparison triangle, if I look at the 3 points X bar, Z bar, Y bar, I actually get equality in the triangle inequality, because the distance X bar, Z bar plus Z bar, Y bar, since this is a comparison triangle, this is the same as the distance XZ plus the distance ZY. And the distance XZ plus ZY, because gamma 1 is a geodesic, that is equal to the distance from X to Y. And because this is a comparison triangle, that's the same as the distance from X bar to Y bar. So we have equality in the triangle inequality. And you can see from the hyperbolic law of cosine, that happens if and only if the angle at Z bar is 0. In other words, this is a degenerate triangle. So these 2 sides have to coincide. So in other words, Z bar has to equal the point W bar. And then by the cat-1 inequality, the distance between Z and W here, W is gamma 2 of t, is less than or equal to the distance between Z bar and W bar, which is 0. So therefore, Z is equal to W. And so gamma 1 is equal to gamma 2. Okay. So geodesics in a cat-1 space are unique. And you can use this to show that, so as you can see here, geodesics are unique. And in fact, if I call the geodesic from x to y gamma sub x comma y, then this geodesic depends continuously on x and y. Okay, and that one can also show using the cat-1 inequality. So if I take sequences xn converging to x and yn converging to y, then the geodesic from xn to yn will converge to the geodesic from x to y. So just an outline of the proof, you can work this out yourself, is given in this picture. You look at the geodesic from xn to yn, you call that gamma n. You take a point gamma n of t, and then you choose a point Zn along the geodesic from xn to y, so that the distance from xn to gamma n is equal to the distance from xn to Zn. So these 2 distances are the same. Okay. Then because the distance between yn and y is going to 0, if I look at the comparison triangle for these 3 points, xn, yn, and y, then this side is going to 0, and these 2 distances are bounded. That will tell you that the distance between the comparison points for gamma n, t, and zn goes to 0 in H2. And then by the cat-1 inequality, the distance between gamma n, t, and zn goes to 0. And then you do the same thing on the other side. I look at the distance from y to zn, and I choose a point along the geodesic from y to x, say wn, which has the same distance as the distance from y to zn. So these 2 distances are the same. And then by the same argument, because the distance xnx goes to 0, the distance zn wn, by the cat-1 inequality, it will go to 0. And so gamma nt is close to wn, and wn will be close to gamma of t, where gamma is the geodesic from x to y, because the distance xn yn is converging to the distance xy. Okay, so that way you can show that gamma nt is close to gamma t as n tends to infinity. And so this geodesic converges to this geodesic. Okay, so once you have that the geodesics depend continuously on their endpoints, then you get that the space, any cat minus 1 space, is in fact a contractible space. So what you do is you simply fix a base point x and you join every point y in the cat minus 1 space to the base point little x, and then you contract along those radial geodesics. Okay, so I mean the explicit formula is the homotopy is y comma t goes to gamma xy of t distance xy. All right, so when t is 1, then you get the identity, and when t is 0, then you get a constant. Okay, and this is a continuous map because this gamma xy depends continuously on x and y. Okay, so any cat minus 1 space is contractible. And for examples of cat minus 1 space, one of the main examples is due to a theorem of Alexandra, which says that if X is a complete, simply connected Riemannian manifold of sectional curvature less than or equal to -1, then X is a cat minus 1 space. So in other words, for smooth manifolds, Riemannian manifolds, cat minus 1 corresponds to sectional curvature bounded above by -1 and complete and simply connected. Okay. So that's one large class of examples, but these are manifolds. The examples, if you want examples of cat minus 1 spaces which are not manifolds, then you can look at metric trees. Okay, so trees are examples of cat minus 1 spaces. Okay, so the next thing I want to talk about is what's called the boundary of a cat minus 1 space. So this is a topological space associated to a cat minus 1 space, which is defined as follows. So we saw that for Hn, we have these two boundaries, right? In the ball model, we have a boundary which is the unit sphere, Sn minus 1. In the upper half space model, we have a topological boundary, which is Rn minus 1 union infinity. Now, both these boundaries are at infinite distance from any point in the inside. Okay, so they're really boundaries at infinity. Okay, and in this model, you can see that any geodesic in the inside, it converges to a point on the boundary as t tends to infinity. Okay, so the boundary we should think of as the ways in which geodesics can go to infinity in the space. Okay. So I should mention it's easy to show that Hn in particular is a cat minus 1 space. That's because it contains copies of H2, lots of copies of H2. So in fact, geodesic triangles in Hn are already comparison triangles themselves. They're isometric to triangles in H2. So the boundary of a cat minus 1 space is, you can think of it as a generalization of the boundary of Hn that we've seen in these two models. So it's defined as follows. So as a set, the boundary is, you look at all geodesic rays in X, where a geodesic ray is an isometric embedding of the closed interval 0 open infinity into X, modulo the equivalence relation of being asymptotic, where this equivalence relation is the following: gamma 1 is equivalent to gamma 2 if the distance between gamma 1 and gamma 2 is bounded. So there exists a constant c such that distance gamma 1 t, gamma 2 t is less than or equal to c for all t. Okay, this constant of course depends on gamma 1 and gamma 2. Okay, So, so the boundary is a set of equivalence classes of geodesic rays. Okay. Now we can look at X disjoint union its boundary. We call that X bar, and we can put what's called the cone topology on X bar. So for this cone topology, we choose a base point X naught in X, and then we say that a sequence Xn in X bar, Xn converges to a boundary point xi if, so I know that there are unique geodesic segments from X0 to Xn. So there will also be a geodesic ray from X0 to xi. In other words, xi is an equivalence class of geodesic rays. In that equivalence class, as I'll mention in a bit, there will be a geodesic ray in that equivalence class whose starting point is X0. So let me call that geodesic ray bracket X0 comma xi. So the geodesic rays from X0 to Xn, these should converge to the geodesic ray X0 to xi uniformly on compacts as n tends to infinity. So that means if I look at any fixed length segment of the geodesics X0 Xn, say the segment of length 100, those should converge as n tends to infinity to the segment of length 100 of the geodesic ray X0 xi. So in this picture, as you can see, here's Xn, it's converging to a boundary point xi. This geodesic ray from Xn to X0 is close to the geodesic ray from X0 to xi. Up when you look at a fixed distance. Okay. So in other words, this a neighborhood of this boundary point xi, it looks like this region here. So it's a truncated cone, right? It looks like a truncated cone. The cone is this whole sector, but you remove this part, the part which is inside a ball around X0. And what is outside this truncated cone is a neighborhood of xi in this cone topology. Okay, so that's why it's called the cone topology. And what one can show is that this cone topology is independent of the choice of base point. Okay, and moreover, X bar, the space X union del X, this is compact if and only if the metric space X is proper. This is a fact. So here proper means that a metric space is proper if closed and bounded balls in the metric space are compact. So for example, manifolds Riemannian manifolds are proper metric spaces. So it corresponds to, I mean, they're locally compact metric spaces. So it's essentially a notion of finite dimensionality. Okay. All right. So let me get back to the notes. So, right. So, so this is what I was talking about just now, that we can join any point in the inside to any point in the boundary. In other words, given any x in X and any xi in boundary X, there exists a unique geodesic ray gamma which starts at X, so gamma 0 is X, and which ends at xi, so gamma infinity is xi. What does this mean? Gamma infinity means the equivalence class of the geodesic ray gamma. Okay. So every equivalence class has a representative which starts at a given point X. Okay. And how do you prove this? So actually for this we need to assume X is complete. So what you do is the following. So you take xi to be, let's say, the equivalence class of some geodesic ray alpha, all right? Now, you let yn be points along the geodesic ray alpha at time tn, where tn is a sequence going to infinity. Okay, so this is the geodesic alpha. It starts at some point y, and then you have these points yn along the geodesic ray alpha. These converge to the boundary point xi in the cone topology. Now what I do is, I have my base point x. I can join x to each of these points yn to get a finite geodesic segment, right? I have a unique finite geodesic from x to yn. The claim is as n tends to infinity, these finite geodesic segments x, yn, these are uniformly Cauchy on compacts, and therefore they converge to a geodesic ray. And then one can check that that geodesic ray is asymptotic to the geodesic ray alpha, and therefore its endpoint is xi. So what really one has to check is that these geodesic rays from x to yn form a Cauchy sequence on compacts. So what one does is the following. You take the geodesic from x to yn, and then from x to some ym, where m is much larger than n, let's say. And then I choose a point along the geodesic from x to ym, m for Madras. So I choose a point z along this geodesic so that the distance from x to z is equal to the distance from x to yn. All right. Now I look at the comparison triangle formed by the 3 points y, x, and ym. So that's this comparison triangle, y with vertices y bar, x bar, and ym bar. Okay. So then there are points corresponding to yn and z on the two sides of this triangle. So there's a point yn bar and a point z bar. Now, this is a triangle in H2 where these two sides are very long and this side is fixed, right? C, the distance from x bar to y bar is fixed. It's equal to the distance from x to y. So using the hyperbolic law of cosine, you can show that for such a triangle, the angle at ym bar, this angle has to go to 0. And also you can show that if the distance from, actually no, what I want to do is I want to choose the distance from x to z to be equal to the distance from y to yn. Sorry, that's what I want to do. So in this picture, from y bar to yn bar is the same as from x bar to z bar. All right. So, so this triangle here, ym bar, yn bar, z bar, this is an isosceles triangle, and this angle is going to 0. And then one can show that the distance between yn bar and z bar has to go to 0. Okay, as n tends to infinity. So this distance is going to 0. So therefore, the distance by the cat-1 inequality, the distance between yn and z, this is less than or equal to the distance between yn bar and z bar. That is going to 0. So that means that the geodesic segments from x to yn and x to z, these will be very close to each other if I look at a fixed length segment of these two geodesics, because their endpoints, the distance between their endpoints is going to 0. So, you know, I can take a comparison triangle x, z, yn, then the side corresponding to yn to z, that distance is going to 0. So then these two sides will stay very close to each other. So that will show that these geodesic segments are Cauchy. Okay. So that's the sketch of the proof. All right. So that's how you get a geodesic ray joining any point in the inside to any point on the boundary. And again, you can show using the cat-1 inequality, such a geodesic has to be unique. Okay. So that's joining one point in the inside to any point on the boundary. Now, similarly, if you take two distinct boundary points, xi and eta, then there exists a unique bi-infinite geodesic. So that's an isometric embedding of the whole real line into x, which start with one endpoint equal to xi and the other endpoint equal to eta. So gamma of minus infinity is xi and gamma of infinity is eta. Okay, so it starts at xi and ends at eta. So what you do is you take your base point x, you take the geodesic rays from x to xi and from x to eta. Then you choose points xn along the geodesic from x to xi and yn along the geodesic from x to eta, so that xn is going to xi and yn is converging to eta. And then you form the geodesic segments xn, yn. Okay. So what you need to show, like in the previous case, is that these geodesic segments are again Cauchy. Okay, so again for that you use the cat-1 inequality. You'll take a comparison triangle corresponding to x, xn, and yn, and here say xm and ym, and then you can choose appropriate points z and w along the geodesic from xn to yn, such that in the comparison triangle, the distance between xm bar and z bar will go to 0, and the distance between ym bar and w bar will go to 0. And so by the cat-1 inequality, the distance between xm and z will go to 0, and the distance between ym and w will go to 0. So that means the geodesic segments xm, yn, and zw are close to each other. And also these geodesics from xn to yn, they pass through a fixed ball around x. So for that, what one needs is actually, if I look at the comparison angles at x between, say, xm and ym, so it turns out that these comparison angles, they actually increase monotonically. So maybe I'll show that in a second. But they increase monotonically, and because xi and eta are distinct points, they converge to a positive number. Okay, so because these angles are bounded below by some positive constant, that means the if I look at the corresponding comparison triangle in H2, then the distance from the vertex corresponding to x to the side from the opposite side, that distance is uniformly bounded in H2 because the angle is bounded below. Okay, the angle doesn't go to 0. So the distance from this opposite side to the vertex is bounded above, in H2. And therefore, by the cat-1 inequality, the distance from x to the geodesic xm, ym, this is also bounded above. Okay, so these geodesics all pass through a fixed ball around x, and you can see that they're close to each other. So therefore, they're uniformly Cauchy, and again, you can pass to a subsequence. Well, I mean, they'll converge rather. They'll converge to a bi-infinite geodesic from xi to eta. Okay, so let me just explain what I said about these comparison angles, that they increase monotonically along geodesics. So that's an easy consequence of the cat-1 inequality. So let me do that here. So comparison angles, monotone along geodesics. So what that means is, suppose I have a base point x, and then I take 2 points PQ. I take two geodesics starting from x, and then I take 2 points PQ along those two geodesics, and then YZ. Okay. So then the claim is that the comparison angle between y and z at x is greater than or equal to the comparison angle between P and Q at x. So how do we see this? Well, what you do is you draw two comparison triangles. First, you draw a comparison triangle for the big triangle, x bar, y bar, z bar in H2. So here's x bar, y bar, z bar. And then you draw a comparison triangle for the small triangle, xpq. So let me give that a different name. So that will be x double bar, p double bar, q double bar. Okay. Now in this big comparison triangle, I have two comparison points corresponding to P and Q. So let me call those P bar and Q bar. Okay. So now notice that the distance between P double bar and Q double bar, by definition, since this is a comparison triangle for the small triangle xpq, this is equal to the distance between P and Q in x. And by the cat-1 inequality, this is less than or equal to the distance between P bar and Q bar, right? So, if I call this angle here theta, and this angle here theta tilde, then notice that these two triangles, the distance from x bar to P bar and x double bar to P double bar, these two distances are equal. And the distance from x bar to Q bar is also equal to the distance from x double bar to Q double bar. So these are two triangles in H2 where these two sides at the vertex x bar, these distances are equal, and the opposite sides, the distance P bar Q bar, P double bar Q double bar is less than or equal to the distance P bar Q bar. That implies that theta tilde is less than or equal to theta. Okay, for this you can use the hyperbolic law of cosine to show this. And what is theta tilde? That's the angle between P bar Q bar at x bar. That's the same as the angle between y bar z bar at x bar. And that angle is nothing but theta tilde is the angle between P double bar Q double bar at x double bar. That by definition is the comparison angle. I'll call it theta x PQ, and theta here is the comparison angle between YZ. Okay. So these comparison angles increase monotonically. Okay, is this all right? Okay, so any questions up to here? Okay, fine. So in particular, if I have this situation where I have two distinct boundary points, well, any two boundary points rather, and I take geodesics starting from x, going to xi and going to eta, and I take points along these, then these comparison angles between x and yn at x, these increase monotonically and they're bounded above by pi, therefore they converge to a limit. Okay, so there is a limiting comparison angle between boundary points with respect to a base point x. Okay, so that's what I mean when I say here, the comparison angles theta x of yz, this converges to theta x of xi eta. That's the limiting comparison angle as y tends to xi and z tends to eta. Okay. So this leads us to define what's called the visual. We want to define now a metric on the boundary given a choice of a base point x, little x. So this visual metric is defined to be the following. Rho x of xi eta, two boundary points, is defined to be sine of half the angle theta x xi eta. Okay. So note this takes theta x is in the interval 0 to pi. So sine half theta x is in the interval 0 to 1. Okay. And one can show that this is actually a metric. So the symmetry is clear and the positivity is not hard to show. What one needs to check is the triangle inequality. So here's a little sketch of proof of the triangle inequality for this metric, this visual metric. Actually, what one can show is if one takes the function, the comparison angle, theta x of xi eta, this theta x is a metric itself. Theta x satisfies the triangle inequality. So how do you do that? You take 3 points on the boundary, xi, say zeta and eta, and you take geodesics from x converging to these 3 boundary points. Now, I take points along these geodesics, y, w, and z, and then I form 2 comparison triangles, x, y, z, and a comparison triangle for x, w, z. So the side x, z, there are sides in these 2 comparison triangles corresponding to the side x, z, which have the same length. So I can put the 2 comparison triangles next to each other to get a quadrilateral in H2, x bar, y bar, z bar, w bar. Now in this quadrilateral, I look at the geodesic from y bar to w bar. So that passes through some point, say p bar, on the geodesic from x bar to z bar. All right. Now p bar corresponds to some point p along the geodesic from x to z in my cat minus 1 space. Okay. And now I also look at a comparison triangle for the triangle x, y, w. So let me call that comparison triangle x prime, y prime, w prime. And so the comparison angles that I'm interested in are the angles here at x bar, theta 1 and theta 2, and at x prime, theta 3. So what I want to show is theta 1 plus theta 2 is greater than or equal to theta 3. But that, if you look at these triangles here, the distance from x bar to y bar is equal to the distance from x prime to y prime, and the distance from x bar to w bar is equal to the distance from x prime to w prime. So again, I just need to show that the opposite side here, y bar, w bar, is greater than or equal to the opposite side, y prime, w prime. Then the angle theta 1 plus theta 2 will be bigger than the angle theta 3. So how do I do that? Well, the distance from y bar to w bar, since this is a geodesic, this is the same as the distance from y bar to p bar plus the distance from p bar to w bar. But now by the cat minus 1 inequality, the distance from y bar to p bar is greater than or equal to the distance from y to p, and the distance from P bar to W bar is greater than or equal to the distance from P to W. And when I add up these two distances, this by the triangle inequality is greater than or equal to the distance from Y to W, which is equal to the distance by definition from Y prime to W prime. So therefore, Y bar W bar, this distance is bigger than the distance Y prime W prime. Therefore, θ1 plus θ2 is greater than or equal to θ3. Okay. And this implies that, so if theta is a metric, taking values in the interval 0 to pi, then it's an easy exercise to show that sine half theta also satisfies the triangle inequality. All right. So this is a metric. So in fact, what is this metric for Hn? So if I look in the ball model and I take my base point to be the origin in the ball model, then what is this visual metric? What is sine half theta? Well, it's very simple. Here's the origin. This is my ball, Bn. I take 2 points xi eta. And I form this Euclidean triangle. So now notice that these two geodesic rays from 0 to xi and 0 to eta, they lie inside a copy of H2, inside this ball Bn. Okay, one can show that. And so the comparison angle here is actually equal to the Riemannian angle at the origin. But now the Riemannian angle at the origin, because this ball model, the hyperbolic metric is a multiple pointwise of the Euclidean metric. So that means that hyperbolic angles are the same as Euclidean angles. So the hyperbolic angle at the origin is the same as the Euclidean angle at the origin. So when I draw this Euclidean isosceles triangle, I'll get two congruent right angle triangles, and this will be theta by 2, and this will be theta by 2. And so this side will be sine half theta by sine half theta, right? In other words, sine half theta 0 of xi eta is equal to half the Euclidean distance between xi and eta. So in other words, this is up to a constant multiple of half. This is the chordal metric on the sphere Sn minus 1. So this visual metric you can think of as a generalization of the chordal metric. Okay, is this clear? So are there any questions so far? I feel like I'm just talking and I don't know if anyone is listening. So
is there any always there is a guarantee to get a comparison triangle for every triangle, no?
That follows from the fact I mentioned at the beginning, right? That if you have 3 numbers which satisfy the triangle inequalities, A, B, C, then there's a unique geodesic triangle in H2 with these side.
Okay.
That's the first fact I mentioned. Yeah.
Okay.
So you always have unique comparison triangles.
Yeah.
That you always have, right?
Okay, right.
Yeah. So any other questions? So what about the definition of the visual metric? Is it clear?
So does this visual metric depend on the base point?
Yes, yes. And the dependence on the base point will be crucial for us, actually. So what happens is, actually, you can see in this picture. So here, if I take a base point which is going far away, like say if my base point was here, then the hyperbolic geodesics would look something like this. And this angle would be much smaller than this angle here. Okay, so as you go far away, the visual metric will tend to 0. I mean, if I keep the boundary points fixed and I change the base point, this angle goes to 0 actually. Whereas if I go close to a boundary point, if I take 2 points which are near each other, say xi and eta are close to each other, and I take an x here, and I'm so this initial visual distance seen from x, it's the angle that you see when you're at x, basically. That's the sine of half the angle. That's the visual distance. That's why it's called the visual distance. It's the angle that you see. So as I go closer to xi along this geodesic, this angle will become bigger. So there'll be a point over here where the angle will actually become 90 degrees. This this angle will in fact increase to 90 degrees. And then as you go towards xi, the angle will tend to pi. As I go further up, the geodesic will start to look like this. So when I'm very close to xi, what will happen? It will look like this. So here's xi, here's eta, and this angle is almost pi. So that means the visual distance is tending to 1, because sine of half pi is 1, right?
Right. Okay, thanks.
So yeah, so it depends crucially on the base point. Absolutely. Yeah. And we'll actually say exactly how it depends on the base point. So for that, we need to talk about what's called the Gromov inner product. So has this been mentioned in the lectures?
Yeah, this has been mentioned in, I think, in the lecture.
Right, on hyperbolic groups, probably, yeah. So it's a very simple thing. I mean, it's this Gromov inner product is a function of 3 points in a metric space. So the Gromov inner product between points y, z with respect to a base point x is you take the distance, half of the distance from x to y plus the distance from x to z minus the distance from y to z. Okay, so in other words, if I take this triangle here, x, y, z, then I add up this distance, x, y, plus this distance, y, z, x, z, minus this distance, y, z. Okay. So that's the Gromov inner product, and then I take half of that. And it turns out that this visual metric, sine of half theta, can be expressed in terms of the Gromov inner product between boundary points. So it turns out as y and z converge to boundary points xi and eta along geodesics, this Gromov inner products y, z, x, they converge to a finite limit if xi and eta are distinct. Okay, so that will be the Gromov inner product between boundary points with respect to the base point x. It's a limit of Gromov inner products from the inside. Okay, and how do you see that? Well, what you do is you look at this comparison triangle for x, y, z. So let me call it x prime, y prime, z prime, and the sides are a, b, c. So here a and b are going to infinity, and c is also going to infinity. And theta, I know, is increasing monotonically, right? Theta is the comparison angle, which increases monotonically. Now I use the hyperbolic law of cosine. So cos HC is cos HA cos HB minus sin HA sin HB cos theta. Now I write cos theta as 1 minus 2 sine squared half theta. So then this becomes cos HA cos HB minus sin HA sin HB plus 2 sin HA sin HB sine squared half theta. And then I divide both sides by sin HA sin HB. Okay, so this cos HC divided by sin HA sin HB, you can see this looks like 2 times e to the c minus a plus b into something which is tending to 1. Okay, as ABC tend to infinity, this looks like 2 times e to the c minus a plus b into something which is tending to 1. And this cos HA cos HB divided by sin HA sin HB, this tends to 1 minus 1. So this gives me 1 plus little o of 1 minus 1 plus sine squared half theta. Okay, and now as these points tend to infinity, this c minus a plus b, this is minus the Gromov inner product, right? Okay, and the right hand side is converging. This 2 sine squared theta by 2, this is the comparison angle. This is increasing monotonically. So this is converging to a finite limit. That means e to the minus 2 times the Gromov inner product, that is converging. So I take and I divide by 2 on both sides and I take square roots. So finally what I get is that e to the minus Gromov inner product yz at x is equal to sine squared half theta into something converging to 1, square root of that. That converges to sine of the comparison angle theta x xi eta divided by 2. Okay, which is the visual metric. So this side converges, so therefore this side also converges. And so we get that e to the minus Gromov inner product xi eta is equal to sine half theta. Is this okay? Okay, so we get this formula. So the visual metric can be expressed in terms of distances in the inside. This Gromov inner product, this is the limit of sums and differences of distances in the inside. Is this okay? Okay. So the next thing to talk about is what's called the Bosuman function. So the Bosuman function of a cat minus 1 space, this is a function of 3 variables, x, y, and xi, where x and y are 2 points in the inside and xi is a boundary point. Okay. So what this does is, so the point xi is at an infinite distance from both y and x, but we can still talk about the relative distance of x and y with respect to xi. So that has a meaning. In other words, what I mean is you take the geodesic from x to xi and take a point z converging to xi along this geodesic ray. Then I look at the distance from x to z minus the distance from y to z. Okay. And I want to take a limit of this as z tends to xi. And the fact is that this limit exists. And that's easy to see because if I take a point w which is after z along this geodesic ray, if I look at the same function for w, so distance xw minus distance yw, then this minus distance xz minus distance yz, from the picture you'll see this turns out to be distance wz plus distance zy minus distance wy, and this by the triangle inequality is greater than or equal to 0. So in other words, along this geodesic ray, this function is an increasing function. This is monotone increasing. If I look at the function, t goes to the distance from x to gamma t minus the distance from y to gamma t. Okay, this function is monotone increasing. And by the triangle inequality, it is bounded above by the distance from x to y. So therefore, it is monotone increasing bounded, and therefore it converges to a limit. That limit is defined to be the Bosuman function of x, y, and xi. Okay. So you can think of it as the distance from x to z. I mean, in other words, the distance from x to xi minus the distance from y to xi. Okay, so let me draw you a picture so that this becomes clear what we're doing actually. So what we're doing is the following. Here's x, here's y, and here's xi. I'm taking the geodesic from x to xi, and I'm taking point z along this. Now what am I doing? I'm looking at the distance from x to z minus the distance from y to z. So in other words, what that means is I look at the sphere with center z passing through x. Okay. So the sphere whose radius is the distance from z to x. And I look at the sphere with center z and radius which passes through y. Okay, so I have these two spheres. And this distance here along this geodesic between these two spheres, this is just the difference between the radii. So this distance here is xz minus yz. So what happens actually as if you do this in Hn or in H2 even, what happens is as z tends to xi, these spheres around z, they converge to what are called horospheres. So in H2, those will be circles, Euclidean circles, which are tangent to the boundary at xi. And one of them will pass through x, and the other will pass through y. And this distance between spheres here, that's what I'm taking a limit of, that converges to the Bosuman function bxyz, which is in this picture the distance between these horospheres. Okay. So that's what the limit is. Okay. All right, so these horospheres, these are nothing but if I fix, let's say x, and I look at the Bosuman function, and I fix xi, and I look at the Bosuman function as a function of one variable y, then these horospheres are nothing but level sets of the Bosuman function. These are level sets of the Bosuman function, all right? And this Bosuman function is the signed distance between the horospheres. So if y is, so a sub-level set of the Bosuman function is a horoball. So that's the inside of this horosphere. So here the Bosuman function will be positive, and outside, as a if y is outside, then it will be negative. So if y is here, so if I take a point z here, then so in this picture b, x, y, xi will be positive, and bx z xi will be negative. Okay. It will be minus this distance. Okay, so is the geometry clear a bit? Any questions?
So I mean, if we vary y and fixing x and y, if we vary y inside my space,
Yes.
so what that will be? I mean, can you say something on the geometry? What is happening?
Yeah, so that's what I'm saying. So if I fix x, then in this picture, when y is inside this horoball, the Bosuman function is negative. Sorry, it's positive because the distance from x to xi is it's infinite, but you think of it as bigger than the distance from y to xi. And if y is outside, like in this picture z here, then the Bosuman function is negative here. And if I take geodesics which converge to xi, so in H2, the geodesics which end at xi, these will be orthogonal to the Bosuman function, the horospheres. These will be the orthogonal curves to the level sets. Okay. And what happens is, restricted to each geodesic like this, the Bosuman function is a linear function of t. It's just a constant plus t. Okay. Right. If I move a distance, if I move a distance 1 along this geodesic, then the Bosuman function will increase by 1. Right? You see from the picture?
Yes.
So along these geodesics, the Bosuman function is linear. It's just a constant plus t.
Okay.
And it vanishes at x, and it's negative for outside. If I go here, then it tends to minus infinity like this. Okay.
Okay.
You can also say it's a one Lipschitz function of y. That you can also say that it's a one Lipschitz function of y. And these lines, these are like gradient flow lines of the Bosuman function. These geodesics ending at xi, in a manifold, these are actually gradient flow lines of the Bosuman function. That means these are the curves of steepest increase. If you go along this, it increases as fast as possible.
I see. I mean, if I consider this, I mean, the geodesic line passing through y and x, so the increasing rate will be on this line, maximum rate.
Yeah, the increasing rate will be 1, right?
Okay.
It will be 1. I mean, the derivative ddt will be 1, ddt of the Bosuman function. Along any of these geodesics, ddt of the Bosuman function will be 1.
Okay.
Along any other geodesic, ddt of the Bosuman function will be less than or equal to 1.
I see.
In any other direction, ddt will be less than or equal to 1. Along these directions, it will be equal to 1. The ones which end at xi. Does this help?
Yeah. Another thing you are saying that this is one Lipschitz. I mean, if I take any y1 and y2, so
Yes. This is one Lipschitz. That you can show from the triangle inequality, because it's a limit of one Lipschitz functions. You see, this as a function of z is one Lipschitz, right? Sorry, as a function of y is one Lipschitz. If I fix x and z, this is a one Lipschitz function of y. The distance function is one Lipschitz, right? So b of x y1 xi minus b of x y2 xi this is less than or equal to distance y1 y2.
I see.
That's just by passing to the limit here. It holds for these finite approximations to the Bosuman function, so it holds in the limit.
I see. So how does this help in the study? I mean,
Okay, right. Now, it helps exactly when we look at visual metrics. So the visual metrics on the boundary, as I said earlier, they are not they depend on the choice of base point, right? When I go close to a boundary point, the angle becomes large. If I go away from the boundary point, the angle becomes small, right? So they depend on the base point. But the Bosuman functions allow us to say exactly what the dependence on the base point is. So that you can see in this picture. So if I look at the ratio of two visual metrics, so I take two base points, x and y. I want to compare the visual metric rho y with the visual metric rho x. So I look at the ratio rho y xi eta squared divided by rho x xi eta squared. Okay. So by definition, this will be e to the 2 times Gromov inner product xi eta x minus 2 times Gromov inner product xi eta y. Now, what is 2 times this Gromov inner product? That will be basically, I take the geodesic rays from x to xi, x to eta, I take points along them, and then I take the sum of this distance plus this distance minus this distance from xi to eta. And from that, I'm subtracting the Gromov inner product xi eta y. So I'll get minus the Gromov inner product xi eta y 2 times. So that will be, I get a minus sign here and a minus sign here, and then a plus sign along from xi to eta. So what happens is the distance from xi to eta, that will cancel out. The distance from xi to eta will cancel out. So what will remain is you'll get a limit of distances, sums and differences of distances. You have a plus and a minus here, and a minus and a plus here. So plus and minus means basically I'm taking a limit as z tends to xi, distance xz minus distance yz. So that is the Bosuman function xy xi. And similarly, I'm taking plus here and a minus here means I'm taking a limit as z tends to eta of distance x z minus distance yz. So that tends to Bosuman function of b xy eta, right? So this difference of two Gromov inner products, it becomes a sum of two Bosuman functions. It becomes, so we get e to the bxy xi plus bxy eta. Okay. So we have an exact formula in terms of the Bosuman function for the ratio between two visual metrics. Okay. And now what I want to do is look at what's called the derivative of one visual metric with respect to another. So what that means is I look at the limit, I fix a xi, and now I let eta tend to xi. And I look at the ratio of visual metric rho y xi eta divided by rho x xi eta. So here x and y are fixed. Eta is tending to xi. And I want to take so these distances are both going to 0, right? They're both going to 0, but it turns out the ratio converges to a finite limit. Because what will this ratio be? At a finite stage, this ratio is e to the half bxy xi plus bxy eta. Now, eta is converging to xi, and one can show that the Bosuman function, as a function of the third variable, the boundary variable, it is also continuous in the boundary variable. Okay, so it is continuous in all three variables. So as eta tends to xi, this bxy eta converges to bxy xi. So what I get is half of bxy xi plus bxy xi. In other words, I get bxy xi. So this limit is nothing but e to the bxy xi. Okay. So let me draw you a picture to help you understand what's going on here. Instead of just symbols, what is going on here? So Okay, what's going on here is the following. So here is X and here is Y. Okay. And here is Xi. And what I'm doing is I'm comparing the visual distances between Y and X near Xi. All right. So if you like, I'm taking a small object near Xi. You think of taking an infinitesimal object near Xi. Let's say, for example, I don't know, a dog. Okay. So suppose there's a little dog at Xi. Okay. I'm sorry, I'm not good at drawing dogs, but suppose this is a dog at Xi. And you're looking at how big the dog looks from Y and how big the dog looks from X, right? The dog is infinitesimally thin. It's a small dog. Now, this limit rho y xi eta by rho x xi eta, this converges as eta tends to xi to e to the bxyz. Now, what is this e to the bxyz? In other words, I take the horospheres based at xi passing through x and passing through y. Okay, and this horospherical distance, this is bxyz. So in this picture, you can see this is positive. So this ratio will be bigger than 1 in this picture, right? What does that mean? That means objects near xi look larger viewed from y as compared to viewed from x. That's because this Bosuman function xyz positive, what this means is that in a sense, y is closer to xi than x. Okay. You think of this as the distance from x to xi minus the distance from y to xi. That is positive, means the distance from x to xi is larger than the distance from y to xi. So therefore, y is closer to xi than x is to xi, even though both distances are infinite. But we can make sense of the relative distance of xi of x and y from xi. All right. And so y in a precise sense is closer to xi than x, and therefore objects near xi look larger when viewed from y than when viewed from x. And we can say precisely how much larger. So if I move up a distance t here, so if this is equal to t, then this becomes e to the t. Okay, so in other words, if I take this geodesic ending at xi, then as I move along this geodesic distance t, objects near xi, as I view them, they'll get scaled by a factor e to the t. Okay, so if I move a distance 1, then an object at xi will look larger by a factor e. If I move a distance 2, it will look larger by a factor e squared. If I move a distance 100, it will look larger by a factor e to the 100. Does this make sense?
Yes.
Okay, so as I get closer and closer to xi, objects look larger. Objects based at xi look larger when viewed from y as compared to x. And by a precise factor, e to the t, right? Where t is the horospherical distance between x and y. Okay. And what does this mean also? That if 2 points lie on the same horosphere, so if y was on the same horosphere as x, then all points on the same horosphere, observers on the same horosphere will see the same size at of the dog at xi. If you're on the same horosphere, then this bxy xi is 0. So this ratio is 1. So for people on the same horosphere, you can think of this as the locus of people who view the dog having the same size at xi. All right? So if you want to move in the space in such a way that the dog doesn't change size, then you will move along the horosphere. That's the only way that the dog will not change size. If you go outside the horosphere, the dog will become smaller. If you go inside the horosphere, the dog will become larger. Does this help now to understand?
Yes.
Yes, and very.
Any questions?
Can I think here, I mean, some kind of vibration over boundary, or I mean, if we change y, so then this number, can I think of them as fiber over some fiber points of H2 or that cat minus on space?
This number bxy xi, this comes up in a when you want to parameterize. Suppose this was a manifold, so then you have a tangent bundle, right? And you have a unit tangent bundle. So I'll talk about this later, probably in the next lecture. You have a parameterization of, so if it's a manifold, then this is in the notes. You have what's called the half parameterization, T1x. This is the unit tangent bundle. This is identified with pairs of points on the boundary cross R. So what is the identification? So you take a unit tangent vector V. Okay. So you can flow along it forwards and you can flow along it backwards. Okay. So you have a forward endpoint, say V plus, and you have a backward endpoint, V minus. So V goes to, so this is a pair, this del 2x means pairs of points on the boundary minus the diagonal. So pairs of distinct points on the boundary. So this goes to V plus, V minus. And what is the real number? I need to say where the base point, the foot of my tangent vector is. That is determined once I know the geodesic, once I know xi, the endpoints, then I know the geodesic, that I know the base point lies along this geodesic joining V plus to V minus. I just need to say where it is along that. So that is determined by the Bosuman function, right? So then I take a B of x is fixed, pi v. So pi v, say v plus. Where pi is the projection from the unit tangent bundle to the manifold. Okay. So in this way, the Bosuman function does lead you to a description of the tangent bundle, the unit tangent bundle. So maybe this is something like what you were asking.
Yes, I think. Yeah.
Yeah.
I'll look at it. Yeah, thanks. Yeah.
So this is called the half parameterization. So I'll talk about this later. Maybe it's in the notes, which I'll share with you after the class. It's in the notes. Okay, so let's go back to the notes then. So, okay, so I think more or less we understand this visual metrics, the Bosuman function, and derivatives of visual metrics. So note that this this derivative is maximum if x, y, and xi lie on a straight line, because that's when the Bosuman function equals the distance from x to y. In general, it's less than or equal to the distance from x to y by the triangle inequality. And it's equal if and only if x, y, and xi are collinear. That means y lies on the geodesic, or x, y, and xi lie on a geodesic. Okay, so it'll either be plus mod xy or minus mod xy, depending on whether y is in between x and xi or whether x is in between y and xi. Okay. Okay, fine. So now the next thing to look at is what's called the cross ratio. Okay. So remember, let's go back for a second to Hn. So in Hn, we saw that the visual metric was nothing but the chordal metric, right? The Euclidean distance between the boundary points on Sn minus 1. So remember, you must have seen the cross ratio in your complex analysis courses, right? So,
Yes.
So if I take the absolute, so that's in terms of products of complex numbers. But if I take the modulus of the cross ratio, that's a positive real number. Then that's a product of distances divided by a product of distances, right? Euclidean distances. Yes? Okay. So that's what's called the Euclidean cross ratio. Now, the Euclidean metric restricted to the sphere is the chordal metric. And the chordal metric generalizes to the visual metric, rho x. Okay. So what we can try and do for a cat-1 space is to look at the same product of distances, where distances are now with respect to the visual metric. Okay. So in other words, if I take 4 points on the boundary of my cat-1 space, xi prime, eta, and eta prime, then the cross ratio is a priori is defined as follows. I choose any base point x, and then I look at this product of visual distances divided by product of visual distances. So it's like the Euclidean cross ratio. So rho x xi eta, rho x xi prime eta prime, divided by rho x xi eta prime, rho x xi prime eta. Okay. So this imitates the Euclidean formula. It's just imitating the Euclidean formula. Now you can ask, does this depend on the choice of base point x? We know the visual metrics depend on the choice of base point, right? We've just talked about how they change when you move. The visual metric gets larger if you get closer to a boundary point. It gets smaller if you move away from a boundary point. But does this cross ratio depend on the base point? Well, it turns out the answer is no. The cross ratio does not depend on the base point. And that's quite easy to see. So what is this product and ratio of visual distances? So each of this is e to the minus some Gromov inner product, right? So basically I'll get e to the sum and differences of Gromov inner products. So let me just draw it in a picture here. What happens is the Gromov inner products will give you, so you have 4 triangles. You have x here, and then you draw 4 infinite triangles from x to xi and eta, x to eta and xi prime, x to eta prime and xi prime. Now the Gromov inner products will basically give you pluses and minuses along these sides of these triangles. All right. So what will happen? For example, this triangle, this corresponds to rho x xi eta, this term here. So that's e to the minus Gromov inner product. So minus Gromov inner product means x to xi and x to eta will come with minus signs, and xi to eta will come with a plus sign. Okay. Similarly, this rho x xi prime eta prime, here x to eta will come with a minus sign, x to xi prime will come with a minus sign, and eta prime to xi prime will come with a plus sign. But now if I look at the other two on the bottom, then this x to xi and x to eta prime, these will come with plus signs from this triangle, rho x xi eta prime. And again from this rho x xi prime eta, this x to eta and x to xi prime, these will come with plus signs. So what happens? All the pluses and minuses in the middle will cancel out. They will cancel out. So what I'll be left with is an alternating sum and difference, is an alternating sum of distances. of infinite distances. Okay. So whenever you have whenever I talk about infinite distances, you have to understand I mean it as a limit. Like the Bosuman function is a difference of two infinite distances. What that means is it's a limit of distances which are going to infinity, a limit of differences of. Okay, so this is a limit of, as I take 4 points which converge to the 4 boundary points, and I take this alternating sum of differences. So a plus here, a minus here, a plus here, and a minus here. This you can see does not depend on x, right? X is out of the picture here. So therefore, we have a canonical cross ratio on the boundary of any cat-1 space. Okay, it does not depend on the choice of base point for the visual metric. Is this clear?
Yes. Yeah.
Yeah, this is fine. Okay. And we have this formula for it. And what you can see is now, this is in terms of distances in the inside, limits of distances in the inside. So therefore, if I have an isometry between two cat-1 spaces, right, then these distances in the inside will be preserved. And so therefore, it's easy to show that any isometry, because it takes geodesic rays to geodesic rays, it will induce a map between boundaries, right? Because geodesic rays go to geodesic rays and equivalent geodesic rays will go to equivalent geodesic rays. Therefore, it induces a map from boundary to boundary. So what this shows is that if I look at the boundary map of my isometry, then that will preserve cross ratios, right? Because these distances in the inside will be preserved. Therefore, cross ratios will be preserved. Okay. So in other words, to sum up now, any isometry between cat-1 spaces extends to what's called a Mobius map between their boundaries. What is a Mobius map between boundaries of cat-1 spaces? It is a map f from del x to del y. It is Mobius if it preserves cross ratios. Okay. Okay. Fine. So let me just say, before going further, let me just talk about, if I have a Mobius map, I can talk of its derivative with respect to two visual metrics. So df will be a positive real valued function on the boundary of x. So with respect to visual metrics rho x on boundary x and rho y on boundary y, this is just a limit as eta tends to xi of rho y of f xi f eta divided by rho x of xi eta. Okay. So I look at the distance in the range divided by visual distance in the domain. I take limit as both of them limit of the ratio as both of them tends to 0. And in fact, one can show this derivative exists. This limit exists and is positive and finite and is a positive continuous function on the boundary. We can even give a formula for this derivative. It's quite simple to do. So how do we show that this limit exists, this ratio of visual distances? So what you do is the following. You choose xi prime and eta prime, which are distinct points which are not equal to xi. Okay. So then I have 4 points. I have eta which is converging to xi, and I have xi prime and eta prime. These are fixed. Okay. Distinct from xi and eta. All right. Now I have a quadruple of points. So I can look at their cross ratio, and I can look at the image points. I can look at their cross ratio. So now I know I'm given that f is a Mobius map. So the cross ratio of the image points, f xi, f eta prime, f xi prime, f eta, is equal to the cross ratio of the domain points. So the ratio of these two cross ratios is 1. Okay. The ratio of these two cross ratios is 1. Now, what is the cross ratio? That means basically it'll be a product. So this distance will come with a multiplication sign. This distance will come with a multiplication sign. And these two will come with division signs, these two sides. And similarly for this cross ratio, I'll get multiplication on this side. On the left side and the right side, I have multiplication. On the top side and bottom side, I have division. Okay. Now this ratio is constant equal to 1 as eta tends to xi. But as eta tends to xi, you can see that apart from these two sides, these small sides which are going to 0, the other sides are going to finite limits, non-zero limits, right? The other sides are going to finite non-zero limits. So what does that mean? That means that this small side divided by this small side, I can take all the other terms to the other side. This converges to a finite limit because all these other ratios, they converge to positive real numbers, right? Is this clear? So therefore, the ratio of these two small numbers exists. The limit of the ratio of these two small sides exists. Okay, and so I can give an exact formula for it in terms of products and ratios of visual distances. Okay, which shows that it's a continuous function of xi also, because the visual distances are continuous functions of xi. So, is this all right?
Yes, yeah.
Yeah, okay. So I can talk of the derivative of a Mobius map. Now, what is the point? And this will be the key point in our proof of Mostow rigidity. So we saw that an isometry between cat-1 spaces extends to a Mobius map between boundaries. All right. Now, the point is for the real hyperbolic space Hn, the converse is also true. The converse is also true. In other words, a Mobius map between boundaries extends to an isometry from Hn to Hn. Okay, so let's look at the case where x and y are Hn plus 1. N is an integer greater than or equal to 1. So Hn plus 1, I'm taking the upper half space model. So it's Rn cross R plus. So here the boundary x and boundary y are identified with Rn union infinity. And the cross ratio turns out to be equal to just the usual Euclidean cross ratio. So this cross ratio on the boundary of a cat-1 space, here the boundary is Rn union infinity. The cross ratio turns out to be equal to just the Euclidean cross ratio in terms of Euclidean distances. And it's a classical theorem, which is easy to show. It's not difficult. That if I have a Mobius map from Rn union infinity to Rn union infinity, any such Mobius map, a map is Mobius if and only if it is a finite product of reflections in hyperplanes and inversions in spheres. Okay, so reflections in hyperplanes are just Euclidean reflections. So these preserve Euclidean distances, so they preserve Euclidean cross ratios. And what is a bit non-trivial is that, so you would have seen inversions in circles in your complex analysis, right? You know how to take the inversion in a circle, right, in 2 dimensions. So that generalizes to inversion in a sphere in n dimensions. Okay. Maybe, is everyone familiar with inversion in a sphere?
Yes.
I'll just draw you the picture. What is inversion in a sphere? So, inversion
tends to 1 by z is kind of an inversion, no?
It's inversion in the unit circle is z goes to 1 over z bar. So it's anti-holomorphic. It's not holomorphic. It's anti-holomorphic. It's orientation reversing. It preserves angles, but reverses orientation. So what you do in Rn is you take any sphere you take the center of the sphere, x naught. You take any point x. Then the reflected point, it's also called a reflection in the sphere, is basically you extend the radius from x naught to x, you extend it to the reflected point x star. This is the reflection of x. You extend it such that the product of these two distances from x naught to x and from x naught to x star, the product of these two distances should be equal to the radius squared. Okay, so if this sphere has radius r, so this is how the inversion in a sphere is defined. Okay, so the sphere maps to itself. On the sphere, the map is the identity, right? On the sphere, the map is the identity. The inside of the sphere goes to the outside of the sphere. The center of the sphere goes to infinity, and infinity goes to the center of the sphere. And radii passing through the center map to themselves. Okay, is it clear?
Yeah.
So these maps, it turns out, this is a computation you can do, they preserve Euclidean cross ratios. This inversions, they preserve Euclidean cross ratios. And conversely, any map which preserves Euclidean cross ratios is a product of reflections in hyperplanes and spheres. Okay, so the Mobius group is not in Rn is nothing but the group generated by reflections in hyperplanes and inversions in spheres. Okay. Now notice, so we're looking at Hn plus 1 and the boundary is Rn union infinity. Now notice my Mobius map of the boundary is a reflection in a hyperplane in Rn, that would be this line in this case, or an inversion in a sphere, that would be this circle in this Rn here. But notice that any hyperplane in Rn extends to a hyperplane perpendicular to the boundary of one dimension higher, and any sphere in Rn extends to a sphere of one dimension higher, which is perpendicular to the boundary. And then the inversion in the lower dimensional sphere extends to an inversion in the higher dimensional sphere. And similarly, the inversion in the hyperplane, lower dimensional hyperplane, extends to inversion in the higher dimensional hyperplane. So therefore, any Mobius map of the boundary, it has a natural extension from the Hn plus 1 to Hn plus 1, which is a product of reflections and inversions in hyperplanes and spheres which are perpendicular to the boundary. Now, this is a fact which is also not hard to show, the classical fact that reflections and inversions in hyperplanes and spheres perpendicular to the boundary, these are isometries of Hn plus 1. Okay? These will be isometries of the upper half space, and conversely, any isometry of the upper half space is a product of such reflections and inversions in hyperplanes and spheres perpendicular to the boundary. Therefore, any Mobius map of the boundary of Hn plus 1 extends to an isometry of Hn plus 1. Okay? So, in other words, to summarize, we have an isomorphism between the group of isometries of Hn plus 1 and the group of Mobius maps of its boundary, which sends an isometry F, capital F, to little f, which is the restriction of capital F to the boundary. Okay, so every isometry inside extends to a Mobius map of the boundary, and conversely, as we've just seen, any Mobius map of the boundary extends to an isometry of the inside. Okay, and this is the crucial fact that we will be using, one crucial fact that we'll be using in the proof of Mostow rigidity, that Mobius maps of the boundary of hyperbolic space extend to isometries of the interior. Okay. Okay, so that wraps up the preliminaries about cat-1 spaces and visual metrics and derivatives and cross ratios. So far there have been no groups in the picture, well, except for the isometric group of Hn. Now I want to look at isometries of general cat-1 spaces, and in fact discrete groups of isometries of cat-1 spaces. And we will be talking about what are called Patterson-Sullivan measures. So these are certain measures on the boundary of a cat-1 space, okay, given a group action of a discrete group. So here's the setup. So suppose X is a proper cat-1 space, and gamma is a discrete countable group, and suppose gamma acts on X geometrically. So geometric action means that gamma acts by isometries and the action is proper. So proper action means that, if you like, one way of saying it is, if I take any point X in X and any compact K in X, then the set of elements of gamma which move X, little x into K is finite. In other words, every orbit intersects any compact set in only for finitely many elements. Okay, only for finitely many elements in the group. So the orbits are discrete, right? The orbits are discrete. Okay, now we're going to make one standing assumption throughout, that gamma is what's called a non-elementary group of isometries. What that means is, the definition is that gamma does not stabilize any finite subset of X union boundary X. Okay, so no finite subset is invariant under gamma. Okay, all right. Then we can define, well, we can define in general for a group acting geometrically what's called its limit set. Okay, so so to define the limit set of gamma, it's so we'll denote it by lambda sub gamma. This is the set of boundary points xi in boundary X, such that xi is an accumulation point of an orbit gamma X. Okay, so the orbit is discrete in the inside because the action is proper. So it can only have accumulation points on the boundary. All right. And it will have accumulation points because we're assuming our cat-1 space X is proper. So X union is, its boundary is a compact space. Okay, and the orbit is infinite because gamma is non-elementary. It does not stabilize any finite subset. So you have an infinite subset of a compact space. It's going to have accumulation points, but those accumulation points have to be on the boundary because the orbit inside is discrete by the properness of the action. Okay. Now you might ask, this set of accumulation points, does it depend on the choice of orbit that I choose? Well, it doesn't, because so this limit set is independent of the choice of X in X, because if I choose another Y, then if I take 2 points in the orbit, gamma X and gamma Y, the distance between these 2 points is equal to the distance XY because gamma is an isometry. So if a point in the orbit gamma X converges to xi, then gamma Y stays within bounded distance of gamma X. And it's easy to see that if you have 2 sequences in a cat-1 space which stay at bounded distance from one another, then by definition of the cone topology, if one converges to one boundary point, then the other sequence will also converge to the same boundary point. Okay, so sequences which stay at bounded distance from each other, they converge to the same point on the boundary. All right. So if gamma X converges to xi, then gamma Y will also converge to xi. So therefore, the orbits have the same set of accumulation points. Is this clear?
Yes.
Okay. All right. So now we define what's called the critical exponent of the discrete group gamma. It's equal to, so you form what's called the Poincare series of the discrete group. So this is a sum over gamma and gamma. It's a function of a variable s. So it's something like a Dirichlet series, but it's not exactly a Dirichlet series. It's but it is holomorphic in a half plane. It is holomorphic in a half plane. It's e to the minus s times the distance between x and gamma x. Okay, and then you sum over gamma. So you look at the s for which this is finite. This sum converges. And then you take the infimum of such s. Okay. All right. So, I mean, if this infimum is delta, basically this series is guaranteed to converge in the open interval from delta to plus infinity. Okay. All right. So this is the critical exponent. It's at the critical exponent, the series may converge or diverge. Okay. We can't say anything at the critical exponent, but after the critical exponent, it has to converge, and before the critical exponent, it has to diverge. Okay. So it's similar to radius of convergence of power series, but here instead of a power series, we have this Poincare series, which is a sum of exponentials instead of a sum of polynomials. So that's all. And this is elementary to show. This critical exponent is, you can in fact calculate, give a formula for this. This is the lim sup as r tends to infinity of 1 over r log of the number of orbit points, a number of gamma and gamma, such that the distance of x from gamma x is less than or equal to r. All right. So you look at the orbit points in the ball of radius r. That typically will grow exponentially. You take log of that, divide by r, and then take lim sup as r tends to infinity. That will equal this critical exponent. Okay, so this is something you can try and show as an exercise. Okay. This is just a fact about series like this. Okay. Okay. And now if X is a complete simply connected Riemannian manifold with sectional curvature less than or equal to -1. So then it's a cat -1 space. Okay. In fact, the Carter and Hadamard theorem will tell you it's diffeomorphic to Rn. Okay. So it's diffeomorphic to the open unit ball, if you want to think of it like that. So now you define the critical the exponent of the space delta x to be the lim sup as r tends to infinity of the log of the volume of the ball of radius r divided by r. Okay, so what happens is by standard comparison theorems in Riemannian geometry, the volume of the ball of radius r will grow at least like e to the n-1 times r, because it'll grow at least as fast as in hyperbolic space. In hyperbolic space, it looks like e to the n-1 times r, the volume of the ball of radius r. And so if the sectional curvature is bounded above by -1, then the volume growth will be at least as fast as the volume growth in Hn. Okay, which is, so it'll grow like an exponential. So you take log of that and divide by r and take a lim sup. Okay. And then what one can show is that the critical exponent of the group is less than or equal to the critical exponent of the space. And if gamma is co-compact, then these two critical exponents are the same, and the limit set is equal to the whole boundary. Yes, sorry, I had a question. Sorry, someone was saying something?
No.
It's okay. Okay, so
Okay.
look, I'm realizing, I mean, this is a lot of material to try and cover in just 2 lectures. So I'm going to skip the proofs here. Okay, so you can look at this proof yourself later when I send you the notes. I'll skip this proof. Let me skip this. I mean, the proof that the 2 exponents are equal when gamma is co-compact. So co-compact means the quotient of x by gamma is compact. Okay. Co-compact means the quotient is compact, but at least it's easy to show the limit set is all of the boundary in that case. That let me just explain. So,
Sir, can you show the definition of the limit set once again? I mean, can you just
it's the accumulation points of an orbit. It's the accumulation points of an orbit.
I just forgot. Yeah, okay, fine.
Right. So, I mean, let me just draw you an example of a limit set. I hope I can draw this properly. So, example, what you do is, so this is called ping pong. You might have heard about this. So you take 2 perpendicular geodesics in H2, okay? And then you know that given a geodesic in H2, in your hyperbolic geometry course, you might have talked about hyperbolic translations along a geodesic, right? Yes, those are isometries of H2. So you take 2 large hyperbolic translations, one along this geodesic and one along this geodesic. Okay. So call that, say, F and G. And then you look at gamma, which is the group generated by F and G. And if you choose these translations long enough, then you can show by what's called the ping pong lemma that this is isomorphic to this is a free group on the 2 generators F and G. Okay. This is a free group on 2 generators. And what will the limit set look like? Well, F will push things near its attracting fixed point. G will push things near its attracting fixed point and away from its repelling fixed point. So, I'm sorry, I can't draw you the exact picture right now. I don't have the skill for that. But what will happen is basically so for example, this fixed point, this will be in the limit set, okay? And this fixed point will be in the limit set, also these fixed points, because these are limits of f power nx and g power nx, okay? Now, if I look at g of f power n, right? So that will also be in the limit set, and g inverse, so that will give me 2 points like this, g and g inverse, okay? And then if I look at, I conjugate, then I'll get 2 points near here and here, and 2 points near here and here, and near here and here, and over here near here and here. So I don't know if you can see it or imagine it, but what you'll get is that the limit set is a Cantor set on the circle. So in this case, this limit set is a Cantor set, which is invariant under the group action. Okay, so this is just one example of a limit set. Okay, so it could be, typically it will be some fractal, it could be, typically it is some fractal subset of the boundary.
Can you say something more how it embeds inside S1?
Well, it's a subset of S1. I mean, S1 is the boundary. So by definition, the limit set is a subset of the boundary, right? So Yes. So, I mean, maybe I should have drawn this picture better for you. So what happens is basically, if I look at if I look at what's the Cayley graph, if I look at the orbit of the origin, right, what's going to happen? It's going to move here, and then this axis of G will move like this under F, and then under F inverse, it will look like this. Okay. And then under the axis of F under G will look like this, and will look like this. And then I'll keep branching out. So basically, if I look at the orbit of these two geodesics under F and G, I'll get a tree. I'll get a tree. And the Cantor set is the boundary of the tree. The Cantor set is the boundary of the tree.
Okay.
So it's, in other words, the set of all, you look at all, you take the graph metric on the tree, and you look at all geodesics in the tree, and then you look at all infinite geodesic rays in the tree. Those will end at points in the limit set, which will be the Cantor set. Does the picture make some more sense now?
Yeah, but my point was, is this Cantor set is kind of dense inside some part?
No, it's nowhere dense. It's nowhere dense. It's a closed subset. The limit set is always a closed subset of the boundary.
Yes.
And in fact, if it has an interior point, then it becomes all of the boundary.
Okay.
So it's always, if it's not the whole boundary, then it's always closed and nowhere dense. It's always closed and nowhere dense.
I see. So if it has an interior point, then it has to be the whole boundary.
Right. If it has some interior point, it has to be the whole boundary.
And how do you conclude that if it has some interior point?
So we'll get to that. Yeah.
Okay.
See, the thing is, look, I made these notes, but this is really the content for maybe 4 or 5 lectures. To do it in 2, I'll have to skip a lot of things. So you can read the notes later. All right. And try and understand whatever you can from the notes. I'll just try and cover whatever I can in this limited time. All right. Okay. I just want to give you a feeling for what happens. I can't do all the proofs. There's not enough time. There really isn't enough time. So, but I want to give you a feeling for what happens. So let me just at least tell you. Okay, so the statement here is that the volume growth of the manifold equals the critical exponent if the group is co-compact. And in general, the critical exponent is less than or equal to the volume growth. Okay. So, I mean, without doing the proof, the heuristic is quite simple. If the group is co-compact, then basically, you take a ball of radius r, a large ball, that will be tiled by copies of a compact fundamental domain, right? All of which have the same volume. So, roughly speaking, up to some constants, the volume of the ball of radius r will be bounded above and below by constants times the number of orbit points into the volume of a fundamental domain. So in other words, it will look like constant times the cardinality of the orbit inside the ball. Okay, so once you take logs and divide by r, those constants will disappear as r tends to infinity, and you'll get equality of the two exponents. Okay, that's the intuition. But then you have to write a proof for it. So I've written a proof, but it's not very difficult. Okay. Is it clear?
Yes. Yeah.
Okay.
Okay. So let me just finish. I'm almost out of time. Let me say why the limit set is the whole boundary. And maybe I have time to say a bit about the classification of isometries. I'll try. So, okay, so given a boundary point, xi, I want to show it's in the limit set. So I know that x is dense in its boundary. the whole space is dense in the boundary. So I can just choose a sequence of points from the inside which converge to xi. Now, because gamma is co-compact, that means there is a compact set whose orbit covers the whole space, right? So that means in particular, there is an orbit. Every orbit is within bounded distance from any point in the space. So given this sequence xn, I can choose for every n an element gamma n in gamma. This is a typo. This should be gamma. There exists gamma n in gamma such that the distance from xn to gamma nx is bounded by some constant s. So if xn tends to xi, so therefore gamma nx, it's within bounded distance from xn, it also tends to xi. Okay. So therefore xi is in the limit set, and so the limit set is the whole boundary. Okay. So for a co-compact group, the limit set is the whole boundary. Now, let me just finish by talking about the classification of isometries of a cat-1 space. So you probably saw this for H2, right? There are 3 types of isometries: elliptic, parabolic, and hyperbolic. Did you see this for H2?
Yes, yes. It is
Right,
discussed.
right?
Yeah.
In terms of fixed points, there's a classification of isometries. So the same classification holds essentially for cat-1 spaces. There are exactly 3 types of isometries. So given gamma an isometry of x, either gamma is elliptic, that means it has a fixed point in x. Okay. So in H2, this would be conjugate to a rotation of the unit disk if this was H2. But in general, you just have a fixed point in the inside. Otherwise, gamma is parabolic. That means it has a unique fixed point in the boundary. Okay. A unique fixed point in x bar, and that unique fixed point lies in the boundary. So there's only one fixed point in the whole compactification, and it lies on the boundary. Then we say gamma is parabolic, or gamma is hyperbolic. Then it has exactly 2 fixed points in x bar, and both of them lie in boundary x. Okay. So for H2, the parabolic case would be, let's say z goes to z plus 1 in the upper half plane. There, the only fixed point in the closure of H is the point at infinity. And the hyperbolic case would be z goes to lambda z, where lambda is a positive real number. There, the only 2 fixed points are 0 and infinity, right? Okay. So this generalizes. So I won't do the proof. I'm running out of time. You can look at the proof. So I'll skip the proof. And I think I'll have to skip this other proof also. Let me just see what comes after. Yeah, all of this, there won't be any time to do. So these proofs you can look through later. Okay, fine. All right, so let me just finish by, so we talked about isometries. Let me just finish by stating one thing which, this proposition, which I won't prove. But let me just finish by drawing you a picture of what the isometries look like. So I guess we're out of time. Okay, so here, 1 elliptic. So in the elliptic case, you have a fixed point in the inside. Now, because it's an isometry, if x0 is fixed, then any sphere around x0 is also fixed, right? It goes to itself because x0 is fixed. So elliptics will preserve spheres around x0. Okay, these will map to themselves. Okay. here the fixed point set of gamma is, well, it contains x naught. It could be larger. I'm not saying there's a unique fixed point. It could have more fixed points. So then there's the parabolic. In this case, there is a unique fixed point, and that fixed point is on the boundary. So here fix of gamma is psi, is a singleton psi. In this case, what happens if you fix psi, then you can show that you have to map horospheres based at psi to themselves. Okay. So what happens is these horospheres, each horosphere will go to itself. Okay, so this will preserve horospheres. This elliptic preserves spheres around the fixed point. This is like a limiting case where the fixed point has moved off to infinity and the spheres have turned into horospheres. Okay, you can think of a parabolic as a limit of elliptics. That happens for H2 at least. And so this preserves horospheres based at psi. And then you have the hyperbolic case. This is like a translation along a geodesic. So the hyperbolic case, you have two fixed points. And this is the case which we'll be most interested in. So psi, which is, let me call it gamma plus, it's an attracting fixed point, and eta, which is gamma minus, which is a repelling fixed point. So the fixed point set is a 2-point set, psi eta. Okay, and what happens is if you fix psi and eta, then because this is an isometry and the geodesic joining psi to eta is unique, therefore gamma has to fix the geodesic joining psi to eta. So then it becomes an isometry of from the real line to the real line, which doesn't have any fixed points. So therefore it has to be a translation. So restricted to this geodesic, it's a translation. Okay. So what happens is it will translate from one direction to the other. So points will move away from eta towards psi. And if I look at, let's say, suppose this was a manifold. If I look at geodesics which are perpendicular to this, okay, then these perpendiculars, this lower perpendicular will go to this upper perpendicular and so on, right? Because it's an isometry. So perpendiculars will go to perpendiculars. And so what will happen is basically, if I take, let's say, any large part of the space minus the repelling fixed point, I take a large part of the space like this outside one perpendicular. Then if I apply a large power of gamma power n, this will map into a very small neighborhood of the attracting fixed point. This will map inside a small perpendicular. Okay, so everything will be moved towards the attracting fixed point and away from the repelling fixed point. So this will contract visual distances a lot. Okay, points which were far apart visually will become very close, contracted towards the attracting fixed point. Okay, so I think this is a good place to stop here.